Swayam Prabha. Digital India. Educated India.
Welcome back. So, we will continue discussing what we started the last class. I will quickly remind you that we have discussed quite a few of hopper feeder in the last classes. One of them is the external gate hopper feeder, as you can see here. So, once again here we have a stationary outer sleeve and the rotating inner sleeve. Sleeve has the slots and the mass of the parts are at the base of this rotating inner sleeve. So, when the rotating inner sleeve is rotating, from the mass of the parts will be nested in the slots, and when the slots will be aligned to the external gate, okay, external gate will be on the stationary outer sleeve, the parts will be falling down. So, here in this analysis what we said is that at a critical velocity the part may not fall and part will actually clog or jam between the edge B and C. All right. Now, if the velocity is below the velocity of the critical velocity, then parts will actually fall through the gate and the gate diameter is equal to the diameter of the part. Now, if the velocity is more than the critical velocity again, then the part by inertia will go through and it will not fall in the gate. So, therefore, only at a velocity lower than the critical velocity the parts will fall, that is what we said. Now, here to get the maximum feed rate, to summarize that, maximum feed rate we could get by the velocity divided by the adjacent slot length, and therefore, to get the velocity, what principle that we have adopted is that the part while moving towards the gate, it is actually covering a certain horizontal distance and at the same time it is falling. Okay. So, since these two times are the same, so if you can find out the horizontal distance and the vertical distance it is falling, they could be equalized, and from that we found out what is the velocity. So, once again let me explain it to you, because this may not be very clear. Like, to find out that from this position, while moving to this position from A to B, how much the horizontal distance the part has covered, this will be equal to d by 2. Okay. So, as we are discussing in the case of external gate hopper feeder, now here what we have to find out is the critical velocity and we know the distance travelled. Okay. So, the critical velocity can be found out from the distance travelled, that means the distance while moving from this position to this position, the part is moving horizontally at a certain distance and at the same time the part is actually moving vertically, that means falling down. So, part is moving horizontally because of the velocity that the inner rotary disc is having, and this distance moved horizontally can be given as d by 2, because this d by 2 is there, and d by 2 we can actually figure out from d minus the d by 2 will be half of the this square minus this hg square. This is the d. Okay. So, this square is equal to this square minus hg square. Hg is the gap between the inner sleeve and the outer sleeve. Okay. Now, since this distance is moved because of the velocity, this critical velocity, though if we divide this distance by the velocity, we can find out the time interval by how much time it has moved. Now, while doing so, while moving horizontally, the part also has fallen down. So, that means it has moved vertically, and that vertical movement can be given by d by 2 minus hg by 2. So, half of that it has gone and half of the d by 2 it has gone. Okay, it has fallen down. See, you can see from here, let us say if it is falling down up to this, it has gone up to the d by 2 and also the half of this distance, all right, half of this distance. So, therefore, this is the distance that it has fallen down, and since it has fallen by the gravity. So, if you divide by gravity, you can find out what is the time. Now, this time during which the part is moving horizontally as well as vertically, they are the same. So, therefore, we can equalize this time, and we can from here solving this, we can find out what is the amount of velocity. Once we found out the amount of velocity, that we can divide by the distance between the adjacent slots, and we can find out what is the maximum feed rate. So, as I said, we discussed that maximum feed rate we cannot get. So, it has to be multiplied by the efficiency. So, if we multiply by the efficiency E, so then we can get the actual feed rate. So, this is the principle that how we can get the actual feed rate, so that it could be matched with the feed rate that the machine requires, assembly machine requires. After that, we have discussed the rotary disc feeder. In here we have the bowl and the base of the bowl rotating, and the base of the bowl we have the slots, and those slots are protected by the ledges here and by the stationary disc. So, that when the parts will be nested on the slots, the parts will not be falling down in this direction or in this direction. Okay. So, there are two types of rotary disc feeder. One is the indexing type. Indexing type is when it will go from one position to another position, it will stop for some time, dwell for some time, so that the parts could be moving down the track, down the slot. And there is another design which is called the rotary disc feeder with continuous drive. In that case, it will be continuously driven, and the part will be different, part will be a disc type, and once only one part will be taken, and that part will be falling down when the ledge will be aligned to the delivery chute. So, there will be no stopover, no dwelling time. Here we can find out the maximum feed rate or the mean feed rate by finding out that how much time it is taken. If a Geneva mechanism is involved, we consider that the dwell time, index time and the dwell time is the same. So, this can be found out from the 2L divided by G sin theta minus mu d cos theta, if you remember that we have done that earlier. So, this is coming from, again this is if you remember, then L we said this is equal to this Ts we found out by doing that half AT square, if you remember. So, here also it is the same way, and we can find out the Ts, this is the time required for either indexing or dwelling, and we are assuming that this is the same. So, therefore, 2 of this Ts, that is the dwelling time plus the indexing time, will give you the complete time, okay, and this is equal to 8L divided by G sin theta minus mu d cos theta root over. Now, this is the maximum time, and maximum feed rate we can get, and that multiplied by the efficiency will give you the mean feed rate of the feeder. So, this we have discussed. Next we discuss the centrifugal hopper feeder, and centrifugal hopper feeder we have the base which is rotating, and during the rotation the parts are given the centrifugal force. Because of the centrifugal force, the parts are nested in the slots which are located at the outer periphery of the inner disc, and when these slots will be aligned to the delivery chute, the parts will be coming out one by one. This is suitable for feeding the plain cylindrical parts like in shown here, and the unrestricted feed rate is proportional to the square root of the hopper diameter and inversely proportional to the length of the part, that we have seen actually in other feeders earlier also. So, if a part is moving with a constant velocity v around the inside wall of a centrifugal hopper, the radial reaction of the hopper wall is equal to the frictional force with the wall. Frictional force with the base, that we have said that if the base is rotating at a higher speed than the velocity of the parts will slip, okay, and over the spinning disc, and then the frictional force on the base will be equal to the mpg into the mu b. Mpg is the part, mass of the part is mp into g, which is coming vertically, that multiplied by the coefficient of friction between the part and the base, and that will give you the frictional force on the base. Now, Fb and Fw, they are the same, we said, because the material of the part, this is the same part, material of the this thing spinning disc and the wall assuming to be same, and therefore, F b is equal to F w. From here we can find out that the v velocity at which the parts are moving, that will be equal to this factor. Okay. So, this you can see that this is proportional to the root over of the d, which is hopper diameter, okay. And this divided by the part length will give you the maximum feed rate. Therefore, we said that the maximum feed rate is proportional to the velocity and the inversely proportional to the part length. Now, the actual feed rate is given by by multiplying this factor with the efficiency, and efficiency into this will give you the actual feed rate, because as we said once again maximum feed rate we do not get. This equation shows that the unrestricted feed rate is proportional to the square root of the diameter of the hopper here, and inversely proportional to the length of the parts. Okay. Now, using the equation of the V that we have said, now the maximum rotational frequency n max of the spinning disc, which increase in the feed rate occurs, is above which, see what we are saying here basically, that we have the velocity. So, from the velocity, knowing this diameter of the hopper disc, we can find out what is the n maximum, okay, the maximum rotational frequency, above which no increase in the feed rate occurs. Okay. So, n max will be v divided by pi d, because pi d into n is the velocity. So, the velocity will be, we have known the velocity, and that divided by the pi into d, this will give you the maximum rotational frequency. Now, this equation if you plot here, all right, in the y axis we have the n max and unit is 1 by second. This is the hopper diameter in meter, all right. So, depending on the hopper diameter and by varying the ratio of these two coefficient of friction, that is between the part and the base and the part and the wall, if we vary them, this will be the curve that if we are using, if we are increasing the hopper diameter, the n max is actually decreasing. Can be used to choose the maximum rotational frequency from here. So, if you have to have the maximum rotational frequency, you know that what is the hopper diameter that you have to select for a particular ratio of the mu b and the mu w. So, this is kind of a calibration curve that is made, so that the maximum hopper diameter depending on the maximum n rotational frequency you can select depending on the hopper diameter. Here there is another hopper feeder. This is quite simple, and this hopper feeder is called the revolving hook hopper feeder, because in this hopper feeder there is a revolving hook which rotates and the base is stationary. So, the parts are at the base, okay, and while rotating this revolving hook will guide the parts along its edge, and at the center there is a hollow cylinder, and that hollow cylinder is acting as a delivery chute. So, through that hollow cylinder the parts will be fed to the assembly machine. So, here of course, the revolving hook velocity is very important, because if the hook rotates at a very high velocity, in that case the parts will not be guided to the delivery chute. Now, there are two more things here. One is this support, which actually is supporting the parts and directing to the delivery chute. Second thing is the disc here. This is the stationary one, all right. This stationary disc is actually preventing more than one part to come to the delivery chute if they are stacked over each other. If the rotational frequency of the hook is too high, once again the centrifugal action prevents the parts from moving inward towards the delivery chute, as I said earlier. Now, there could be another design in the revolving hook hopper feeder, where the hook is stationary and the base rotates. So, that is called stationary hook hopper feeder. And the next hopper feeder is the bladed wheel hopper feeder. This is another design. Okay, there are various designs of the hopper feeders, and you have to select one of them depending on the type of your production, depending on the type of the part that you are actually feeding. Over and above of these designs, the idea of giving you these designs is that you can design your own feeder as well, depending on the part that you are having, okay, that you have to feed. So, let us see the bladed wheel hopper feeder. Bladed wheel hopper feeder is a very strange design, in the sense that this bladed wheel actually does not pick up any part, or it does not take the part to the delivery chute like we have seen in earlier hopper feeders. Here there is a hopper, okay, as it is shown in this figure, and at the base of the hopper there is a mass of parts. There is a track here. The silhouette of the track is the same, or the shape of the track is the same as the shape of the parts, and when the parts will be on this track, this wheel while rotating, this will agitate the parts to be on the track, and if there are more than one part stacked, so then the rotation of the blade will actually remove the other parts except the one which is nested in the track. The rotation of the blade is just above the part which is nested on in the track, and it will only agitate the parts. It will help by agitating the parts to be nested on the track. Here the track inclination angle, here this angle is about 45 degree with the horizontal, and the maximum linear velocity of the blade tip is about 0.7 meter per second. Because as you understand that it is not doing anything rather than agitating the parts, and if there is no blade, for example, then the parts are amassed there and it will not be able to come out of the slide down the track one by one. So, in this the blade while rotating, this is actually helping. This is a simple design, but this is effective, and it will help the parts to come one by one. Here if you read this, rotation of the wheel agitates the parts in the hopper and causes parts arriving at the delivery point in the wrong attitude to be pushed back into the mass of the parts. Okay, because as I said that the silhouette or the shape of the track is the same as the shape of the part. So, part which is not accordingly or not in the right attitude, they will not be nested properly on the slot, and therefore, what will happen while this blade will rotate, it will actually take it off the track, all right, because it will be protruding out, it will not be sitting, not be nesting, not be nested in the track, all right. So, that is the reason that why the wrongly oriented parts or wrong attitude parts will not be coming through the slots, through the slots of the track. This is used for basically nuts and the cylinders, small engineering parts. Now, this is very important because during the assembly, it is the only small engineering parts like nut, bolts, washers, cylinders. So, these are the most of the parts are like that, and they have to be fed, and they have to be fed in the right orientation. So, in that case, these kind of hopper feeders come very handy, and they are cheaper, and their maintenance and other things are not very expensive. Another design of the hopper feeder is the tumbling barrel hopper feeder. So called tumbling barrel hopper feeder is a combination of the vibratory bowl feeder and a normal tumbling barrel. So here what happens is there is a barrel here, that barrel rotates, all right, and inside the barrel there are vanes. Those vanes actually, while rotating, it will take the parts from the base of the barrel where the parts are located, and while going up or rotating further, the parts will be falling from the vanes to the track which is going through the center of the barrel, and the track is vibratory track, and it works as a vibratory rail based on the principle that we have discussed in the vibratory ball feeder. That means, there is a vibratory drive unit here, which vibrates that rail as we have discussed in the vibratory ball feeder, and because of the vibration, the parts are hopping and then going forward the rail when the parts are falling from the vanes as the barrel is rotating. Okay. So, this is a very simple design, again suitable for feeding a wide variety of parts, for example, cylinders, U-shaped parts, angled parts, prisms, etc. And depending on the type of the part, you can design the vibratory rail, that is the silhouette of the vibratory rail, shape of the vibratory rail, so that also the rightly oriented parts can be actually nested. That is also is possible. Okay. Here is one example of the kind of a part that fed through the vibratory rail, length and the diameter given. So, vibratory rail, when you are actually selecting, if the diameter of the part is this, so this is the 1.2 dia and this is the 0.5 diameter. So, this is the shape of the vibratory rail, how you can design depending on the part that you have with a certain diameter and with a certain length. Now, performance of a tumbling barrel hopper when feeding cylinders is given graphically here. So, this is for the velocity between 0.04 and 0.1 meter per second, and this is the modified efficiency here, and this is the ratio of the L by D, that is L is the length of the part and D is the diameter of the part. Okay. So, this kind of curves are, as I said, they are normally given as a reference curve, so that you can find out or select the efficiency. For example, here it is the efficiency which is given. Okay. Yeah, this is another center board hopper feeder. This is called the rotary center board hopper feeder, and here the principle is different than the one that we have discussed here, for example. See, they are very similar to that. Look at this once again, bladed wheel hopper feeder. This blade is not selecting the parts, it is agitating the parts. Okay. Whereas, in this case, for example, what happens, the same kind of a ball, all right, hopper, and at the base of the hopper we have the parts. Now, here this kind of hopper feeders are particularly suitable for the U-shaped parts, like here, like it is shown here. Now, the rotary bladed wheel, which you can see here, this rotates, let us say this is rotating in this direction, and while rotating through the mass of the parts, it will actually pick up the parts, okay, because the parts are of the U type and they will be picked up by the blades, and let us say in this position where one part has been picked up, and if it is rotating in this direction, that means part will be coming from here to here, and while it is here, the part will be sliding down this, and when it is aligned to this delivery track, the part will be coming through the delivery track. So, this is also a very simple design, and as you can see that not all the time the number of parts will be the same. So, therefore, when you are finding out the average feed rate, you have to multiply by the efficiency, and again efficiency you can find out experimentally by rotating few times and find out that how many parts on an average it is coming per rotation. So, once again this is not agitating, the rotation of the wheel is not agitating the parts, but actually it is picking up the parts from the mass of the parts, and because of the profile of this blade, the parts which are being picked up on that while rotating, this part will be falling from here, and if it is aligned to this delivery track, the parts will be coming down. So, here the edges of the blades are profiled to collect parts in the desired attitude. Another very big advantage of such kind of feeders is that parts will always be delivered in this orientation. It will never be in other, it is not possible. So, therefore, here there is no reorienting device which you require, and if this is the desired orientation which should be coming to the assembly in this way, so then This is the very big advantage of the hopper feeder, because it will be coming at a particular desired orientation and always it will be available in that orientation only, and later to slide off the blade, as I said. So, some of the next feeders and characteristics we will discuss in the next class. Thank you.